Good evening, Nashket ji.
Good evening, Amit ji. So let us we'll start the session then. At very good evening to all the participants. We are welcome to the third day of the AICTE ATAL FDP on future perspective of AI and data sciences. algorithm applications. For this session, we have with us Dr. Amit Kumar Singh as the guest of speaker. Before he starts his talk, let me take the privilege to introduce him. Dr. Amit Kumar Singh is distinguished professional with over 16 years of experience in Indian Space Research Organization ISRO, currently serving as Deputy Project Director for Chandrayaan-4 and the Human Spaceflight Program. He has contributed over 15 critical missions, including Chandrayaan-3, the Mars Orbit Mission, and Aditya L1. His expertise spans satellite health monitoring, AI/ML-based mission management systems, trajectory design, and end-to-end ground segment automation. Dr. Amit holds a PhD in artificial intelligence and has undergone extensive training in mission design, AI applications in orbit mission mechanics, and control system. His innovative work in automating mission operations and integrating AI for spacecraft health monitoring has been transformative in reducing operational deficiency of the space missions. He has authored several technical papers on topics such as anomaly detection in spacecraft telemetry, satellite health monitoring using AI/ML techniques, and orbital trajectory optimization. His research includes notable work present at prestigious conferences like AICTE, AICC, and KDD, along with publishing articles he has published articles in journals like ACTA Astronautica and Journal of Astronomy and Astrophysics. With this small introduction, I would like to hand over the session to Dr. Amit.
Yeah, good evening to all. First of all, thank you, Dr. Nachiket, for inviting me. And I'll try to present my PPT. If you can remove, yeah, thank you. I hope PPT is visible.
Yeah, it's appearing. Yeah, now it's clear. Coming full. Yeah, you can start.
Okay.
Yeah.
So, welcome all of you. I'll try to cover the application part of AIML as of now in the space mission management in ISRO. As you are aware, the ISRO is having one center called ISRO Telemetry Tracking and Command Network, which is situated in Bangalore in the Pune industrial area, which is responsible for managing all the spacecraft mission operations, starting from pre-launch simulations, launch, early orbit phase, initial phase, and then going to the normal phase of the operation. So STRAC is taking care of this all, providing all ground segment and carrying out the mission operation during all phases of the mission. Either it is low Earth orbit or interplanetary missions. And if it is a geostationary mission, the control center exists at MCF Hassan, Master Control Facility, which is there in the Hassan district in Karnataka. So I'll be focusing mostly on the low Earth orbit mission management and the interplanetary mission management. And my presentation will go like this. I'll be starting with some introduction, then giving the space AI role in mission operations, scope, and these are the topics as we go. So I'll just, since I was not knowing what kind of audience I'm going to face, that they are aware of the all full segment, ground segment of the mission. So I just put one introductory slide. So generally, any space mission, if you see, it contains three segments. First is the launch segment, where the rockets comes to the picture, which takes the satellite into the space. And then come the space segment. Space segment is once the satellite is injected into the orbit from the launcher. So this we call as a space segment, and the ground segment is the satellite in this space. This is all represent the space segment. Remaining all the bullets which is shown here is all the part of the ground segment, starting from the reception of the RF signal at the earth station, and earth station takes the demodulate the data, and then again it transmit through the communication links through the computer servers, storage system, networks, and it reaches to the control center. And in the control center, the most important operation which starts from for any mission is starting from the satellite mission design, and conceptualization, like how the mission should go and how it should be managed. And then the orbit dynamics, there comes the our trajectory optimization, trajectory design, what kind of attitude satellite will have. And then comes the network and satellite scheduling process, like if you have a 10 antenna across the globe, so how that 10 antenna will be utilized throughout the orbit, so that scheduling part is done. And then the finally is satellite operation to manage the mission to keep the spacecraft in the healthy condition, like some thermal variation, making some payload on, making the maneuver to take the payload images to carry out the intended operation. So those things is being managed under the operation planning. And once planning is done, then this command is being generated, and which has been transferred to the real-time processor, where the commands is getting converted, and again it is routed to the same backward chain, which gets transmitted back to the satellite. And once the satellite is done the payload, again through this chain, the payload data, which is a very high data rate data, it may be around, as of now, the maximum data rate which ISRO is initializing is around 946 MB per second, which is getting received again and coming to the payload data center, which goes for the image processing at the ground. So as of now, you can see there are some anything which is flowing is the data. And once we talk about the data, which we are trying to visualize, something is happening somewhere place. The analogy you can see, for example, if most of the people, if they are not familiar, you are trying to operate something using the remote, like in our home, we are setting the AC temperature in the remote, and temperature gets changed in the our split AC, which is mounted at the top. So here difference is the satellite is at around 400 500 kilometer away, so we need the bigger antenna to transmit that command, that whatever you want to set or whatever you want satellite to do, you have to communicate through the bigger antennas. And once you communicate to the satellite that what he has to do, it will perform the task as per your the command. And once the task is performed, the output data again it comes back to the control center. So total game of managing the space assets and space mission is centered about the data analysis, data distribution, and the insights from the data. These are the three major elements which is driving the full space mission across the globe, across the space agencies. And when you talk about data science, data engineering, you cannot be nowadays. It's but obvious that you will go in the field of AI/ML. So how AI/ML is important and what key role they are playing in this area as of now. All the space agencies trying to encash and trying to reduce the effort in mission management, even in the product generation and deriving the insights from the payload data. So this is the major elements which we have started. So mostly I will be focusing in the space mission area. Data product I'll be not touching because that is a different domain itself. So enhanced telemetry monitoring, analysis, and identifying the anomalies in real time, the is a very critical pass. If you see any satellite across any ground station, so what happens is throughout the day it comes around only 5 minutes, 10 minutes to 20 minutes across any ground station in 24 hour. So within that 10 minutes you have to decide what is the health of the satellite, and accordingly you have to take the action if anything goes wrong. And within that 10 minutes you have to do that what satellite has to do in next 24 hours. So that timing each second is very critical to do what operation whatever operation you want satellite to do, or whatever way you want to manage the satellite. So definitely this is not the task of some human being sitting and analyzing the data in real time. There must be some system, some software, or some tools, or some models which should be taking the telemetry data in real time as a stream and analyzing on the run, and providing the insights in the data that yes, I'm okay or I'm not okay. And if some action has to be taken, that action has to be done. So these are the activities where we see there is a lot of potential, where advanced AI/ML based techniques like NLP, LSTM, time series data analysis tools, and then the new anyway transformers are coming. So that is another milestones. So that gives a lot of scope in improving our mission management operation. So and in that, another tool comes when we are going for the decision making, like let us say I have seen that there is some problem in the onboard, some sensors, there are at least some 200 to 300 sensors, including all attitude sensors, then thermal sensor, pressure sensors, those readings, if anything has gone wrong, you have to decide and take the redundant, enable the redundant sensors, or you have to do the corrective action. So those kind of decisions, the predictive models also gives a lot of foresight into managing that there is something is going to be wrong, which we can prevent in the advance. So that techniques are also very useful. And since the, as I told, the data which we are recording as a payload, it is in mbps, like 900 mbps, 1 gbps. So a lot of data is getting transmitted at the ground, which is of no use. If you see, if I process the data on board itself, so total data transmission rate will be in some kb or mb, because that is the final output. But the raw data, it has an enormous amount of informations which has to be processed at multiple level, then finally extract the actual information. And if you able to do all this process on board itself, the transmission data rate requirement will come down, which will save a lot of resources, starting from your antenna size, computer network, communication links, all these things requirements will go down. So as of now, the onboard processing of the payload data is also is they're taking so much interest in the space community. So some people have started making the satellite which is having AI processing on board, which is used for the image processing and providing the data directly to the user. And then there one more concept has come, that sensor modeling and control system modeling. So some satellites which is having AI based control systems, and some sensor which is estimating the data, which is estimating the sensor data on board itself, so we don't need the hardware. So initially one of the satellite has been launched by us, which is having full AI based tool and controls and the sensors which has been already modeled. So these are the key area where AIML is playing a very important role. So if you go for the mission operation management, there specifically there are four kinds of area, where one is the telemetry monitoring, then smart operation agent, like in real time, if you want to have some guidelines, you can chat with the chatbot, or you can talk to the chatbot and get the final conclusive decision that yeah, this you have to do, or this information I have to convey, or this is the critical things which I should focus on. And then coming to the flight dynamics operation, flight dynamics, if it says, as I told in the start slides, it's totally is the determination of position and velocity in the space. And this is another estimation in conventional way. This is all estimation process, where we are getting some measurements from the ground station, and then we are estimating what is the actual orbit of my satellite. So that also here in the, if you go for the lstm, that is a very potential application for reducing the workload which is done by the flight dynamics team. And then we are going for the next level, which is called predictive system maintenance, using the tools when we are going to predict that yes, based on this condition earlier mission, some system has failed, so this system is showing some signature that it is going to fail. So we can take some action in advance to prevent that failure doesn't happen. And then payload data processing and onboard processing. So this I will be just showing you how we are doing in the ISRO, and what way we are reaching, and what all the issues we are facing as of now. And just for information, I'll tell from ISRO, nowadays there is a program going on, you may be knowing, that is called Respond. So through that also multiple problems of this area is being published in our yearly booklet, where academia can participate to resolve the challenges which is given as a problem statements, and it is open for all academia to participate. So this is the AI roadmap which is going as of now in our stack here in ISRO in operation area. First is the health monitoring, then smart operation, then going for mission management, and then going for the predictive. So this is the milestone which has been established, I mean set up by our team, and they are working as of now in the all these four area. So I'll just show you the glimpse in what area we have gone for, what kind of application, and what is the output we are getting. So now the what is that? Let us say, if I say in mission operation, why we want AIML? Earlier, using the conventional softwares, we are able to manage the mission. Then why you want to go for AIML? That is obvious question. So what happens is, if you see any hardware or any design part, if anytime you do, it is very dependent on the person who has designed and how it to work. So what happens once that person is something he has designed, and transferring that knowledge to somebody else is another Herculean task. So what is the main goal that somebody has told me that I have designed this particular sensor which has to operate between X and Y limit, and within XY limit its status is normal. So what we do in earlier that rule based system, that is out of limit based system, we said that okay, X and Y, if it crosses, you give me the alert. What happens if the pattern within the XY it changes and it goes irregular? So that is the one signature that yes, this sensor is going to be, or this system is going to be having some problem in the future, and that you have to do. And in a satellite, in one general satellite, if you see one typical satellite, we have around 8,000 to 20,000 parameters to be monitored. So putting limits for each parameters, like around 20,000 parameters by the designer, it itself is a very, I mean, difficult task, because whatever simulation and whatever design they have done on the ground, and when it goes to the space, those designs had the variation. So if you set some limits based on the ground design, which may not be applicable once it goes to the space, there will be some changes. So tuning this by manually is another challenge. So here in the data engineering, what we call is another technique called non-parametric dynamic thresholding, where from the data itself we try to derive what should be the pattern when we declare it as this is my satellite is nominal, and derive those patterns, derive those limits, and derive that whatever condition is this system is operating, and based on that you define something which is good for the people who are going to operate the satellite in the future. So they need not to worry much about the what part of the design has considered, what kind of environment has been considered for the design. So that is another bigger advantage of using AIML in this area. And another problem comes in our mission operation is, if you say something X is right or X is wrong, you have to give the proper justification and reason that why you are saying that it is wrong. So now the new concept of this explain level AI, which is has become very useful for inferring the background information that why we are saying that this decision, this particular system is wrong or right. So that has also given one more confidence to move in operation and in mission area to the our AIML domain. So what frameworks we are working as of now in this? This is the five pillars which has been decided. I mean, which has been designed. One is data insights. Once you get the telemetry data, how the data is going to behave. So you try to analyze, which includes first, since as I told, there are some 8,000 to 9,000 parameters in a satellite. All 8,000, 9,000 parameters are not independent parameters. There are multiple parameters like state of the satellite, it is in sunlit condition, it is in eclipse condition, it is near north pole, it is near south pole of the earth, or it is seeing towards the sun, or it is seeing towards the earth, or it is seeing towards the moon. This all we call as the state of the satellite. So based on the state of the satellites, the pattern which is being followed by all other parameters varies. So what we try to do, once you get the data, first you clean the data that there is no noise in that, and then you find the correlation between the parameters, that based on the state what kind of pattern I am expecting. So there comes the dimensional reduction, where we try to correlate the parameters and try to find out the important parameters, and we drop all the parameters which are almost showing no significance in monitoring the health and deciding some operation of the satellites. And then there are some instruction which is being sent day to day basis for the payload to carry out different kind of operation. So that is called another state of the payload, and based on the state of the payload parameters also varies. So this command to telemetry parameter mapping is also another important task, that if I have given some command X, which are the parameter I'm expecting to change and what way it has to change. This mapping also we can do using this correlation techniques in the our data science. So that also being done. And then the specific events, like sometimes we are trying to raise the orbit, we are trying to go 1 lakh 2 lakh away from the earth. So those kind of events is specific monitoring, those also is one class. So these are being done from the data insights, and then further if anything is getting deviated, so alert is being generated from there. Next comes the decision making. Once you have the insights from the data, so now you have got the data that something has gone out of bound, or something has gone, something is within limit. So once we say it is normal, how it is normal, what is the context it is normal? Like I'm doing some special kind of maneuver, rotating the satellite, or doing some calibration exercise. So in that case my parameter may vary, which I don't know that earlier I have done this kind of activity or not. So those kind of context has to be analyzed, and then that also has to go into the decision making. Once I'm telling that the sensor is behaving abnormal, and but the condition which is now is there for the satellite is not known to me earlier, so immediately some predefined actions should not be taken by the person who is sitting and managing the satellite in real time. He should not get prompted to take some action which may not be relevant in this condition. So those kind of conceptual, then translating the data to the specific action, and then applying that insight to the action, and that it will give me proper output or not. So this kind of extraction is done by this another agent which we are connecting here. And another one comes the AI assistant. AI assistant is nothing but is the combination of all these four pillars, other pillars, where he is having the information about all this action which is happening, and it is having all the information from start of the mission documentation, design parameters, planning and analysis, and then he's having real-time telemetry data. Is having database. This SIMS stands for Satellite Information Management System, which is having data across the mission, across the design phase, across the initial phase, which is getting fed to here, and then monitoring of the status of ground segment, like which antenna data is sending, from where data is coming, not coming. So those informations is being fed, and this AI assistant work as a parallel controller to the person who is sitting to next, and he can interact with this for whatever information he wants to know. So this is another very I mean, I can say that the world which has brought the chatbots, they are very helpful in this kind of application in mission management area. And then AI planner is nothing but it's kind of scheduler, which is another reinforcement learning based scheduler, which is taking care of all the conditions and then planning for the next operation which he has to do tomorrow or next day. So those kind of information also is being done by this. Okay, and the optimal utilization of ground resources also is being done by this particular agent. And mission analysis, this is a very important part, which is starting from the initial, which is having multiple wings, like starting from the data driven analysis, like some mission I want to design which is going to be in 500-kilometer orbit. So first what we see is where is that is there any mission which has been designed earlier using this configuration in 500-kilometer orbit or not. If it is driven, how the data variation has happened, how the sensor has behaved. So those inputs goes to the data driven analysis. And then comes the flight dynamics parts, where we go for orbit prediction, orbit determination, trajectory optimization. And then nowadays there are a lot of satellites in the space in every orbit, so we have to avoid the collision between the satellites. So that is also coming as another part in our mission design, that how to select the particular orbit where less constellation is there, so the probability of collision is also less. Then going for simulation and modeling, and then predictive maintenance. So these are the factors which is going in this management. And let us move to the some application cases, how we have designed this, and how we have proceeded further. So these are the things when we are going for the telemetry monitoring. How, what is the criteria? How to select their multiple models? Which model is suitable for you? So we have gone through almost a lot of models. You can see this outlier probability based on intrinsic dimensionality, then DB scan, low cut outlier, where we are going for statistical restriction. And the problem what we faced in this is when we go for statistical measurement, if the noise is more in the data because of any reason, that signal strength is poor, there is a rainy season, antenna is not able to receive the proper RF signal, so that our telemetry data gets corrupted. So the performance of this statistical based model goes, into the problem that it doesn't give proper output. So yeah, from there going to the supervised learning, then again, some what is the problem we faced in supervised learning is, if I have it, let us say 20 satellites, out of 20 satellites in 5 years, only one or two satellite has gone into the some problem. So I don't have that many states to train the model that this is all my anomalous cases. So ground truth is very less available. So this model also, and then another one is this CNN based image based model, where some people have shown that for time series analysis we can generate into the image, and then image comparison can give me the proper output for anomaly detection. It works for the ground system because their noise transmission from the sensor to the storing devices and analysis devices is very nearby, and there is no uncertainty that I will get noisy data. So this kind of image processing also works there well. But when you go for the 6 kilometer 600 kilometer and all in the space, this uncertainty gets increased, and the images will have some jitter in the in the plot when you plot the data. So there also this kind of techniques was started failing. Then we have gone finally to divide some parameters which can be digital or static, which is not changing, so that we can go for statistical models, and some which is our analog parameters, which is is having continuous variation, so we can go for deep learning and dynamic thresholding. Then we can go for adversarial network, and we can try some transformer also. The most important of the transformer is, what we have seen is, if you train for one satellite which can detect change in the data, time series data, it can be applicable for all the satellite irrespective of the parameter. So that is one very good example, very good case has come from this transformer based algorithm, and nowadays we are using for almost all satellite. uh, so, okay, this is another part how this non-parametric dynamic thresholding is being generated, which where we are taking the predicted value and actual value, and trying to compute the exponential weighted to smooth the errors, and then trying to find out what is the mean and what is the deviation of this parameter from the nominal behavior. And then we try to estimate that this parameter is varying from full training period, what is the variation, and based on that we decide what should be my epsilon. So epsilon is nothing but it's a deviation from my mean value by compared by the standard deviation. And standard deviation, the parameter z, is being selected for each parameter automatically based on the variation during the training time. So this gives one advantage, like if you have 20,000, 30,000 parameter, you need not to see the data, just run the algorithms, it will try to find out the thresholding. This is one crude way, but it works most of the cases. So when we go to adversarial network, what we have tried is, as you all know, that it is based on the generator and discriminator. We try to feed the actual telemetry data to the discriminator, and the generator tries to replicate, and the errors which comes is try to, if is able to detect that this is a real signal, then there is no anomaly. The moment it start detecting that this is a fake signal, we declare it as anomaly. So this is a training setup, and then finally we put into the our operation area where we try to detect all this. So this is a standard picture, which is for the transformers, where is the attention model comes. The most of the important part of this attention model, what we see, as I told earlier, there are multiple parameters which is depending on the state. So how to tell that which parameter is having more impact when I'm going to the payload state, or I'm going to the sunlit sun weaving state, or I'm going to the eclipse state, or different state, which parameter I should be able to focus more. This is very helpful in that case. So this is also a kind of very good application in space mission. So this is our overall architecture, how we have made this overall AI in the operation system. We are taking the raw telemetry data, pre-processing, storing the process data. This data goes to the different AI model. So here what happens is, since as you told, the satellite system is divided into the multiple subsystem, like attitude orbit control system, then sensor subsystem, then power subsystem, thermal, pressure subsystem. So like that we have different subsystem, and each subsystem is having multiple pits. So what we have done is we have decided each model for individual pits parameter which is at very low level, and then combining all the pits we have made another model which is called subsystem based model. And like this we have multiple subsystem model, and then overall one model is sitting for the satellite. So there are three layer architecture which gives me the full replica of the satellites. And once the satellite full model is processed the data and it has detected something, it will generate the limits, it will generate the status, and based on the decision taken by the another trained model agent which is sitting outside, which is having information of all the events which has happened across the satellite, across the mission, and what is happening as of now in the real time in the data. Based on this it takes the decision, it will inform to the particular person who is sitting to the control in the satellite. And this person, if you want to infer further, you want to investigate further what is happening, he has interface to go to the chatbot, and from there chatbot has access of all this information, and he has access of the all mission documents. He can find the query, fire the query and get the output, and based on that he can take the decision. If you want to do some analysis also, you can do through this tool. So this is the another implementation architecture. So how this things has helped in our real-time environment. So this is another plot of SADA, that is called solar drive assembly, which is moving our solar panel, which is used for the power generation. So generally it has to generate the constant power of 12.5 ampere. But suddenly some days what happens when it has gone to eclipse, this is the eclipse means I am not able to see the sun, that is the state of satellite. So there definitely there will be no power, so power generation has gone zero. But when it came out of the eclipse, means when we started seeing the sun, the power generation should get maximized. But what happened, it has maximized for certain duration and then again it has gone into the zero state. So this indication was not expected. When I am seeing the sun, I should generate constant power. So these systems are able to detect those kinds of changes. This is the anomaly score which is plotted in the orange, and we are trying to find out whenever it is crossing 30%, we are generating the alert. So based on that, the systems are able to detect this is anyway, this is large scale anomaly. So this is another typical case of another satellite, which is astrosat satellite for astronomical observation. We have a mechanical wheel which is rotating at around 4000 rpm, and when it is aged around 5 years 6 years, it started giving it's the problem in the friction. Since it is a bearing kind of mechanism, it starts generating the friction. But the friction when it starts, it's a very low level. You can see the scale is plus minus 0.04, it is second degree. And when and the nominal case also, it is varying in the same order. The variation is also in the plus minus 4. But what happens after the certain particular time, this starts showing the high frequency component, that too at very low level. Its level is around 10 to power minus 6, but it shows that this wheel is degrading and is going to fail. So this kind of indication using the out of limit is not possible. So this model which is trained to predict, you can see here, it is predicting that your noise has gone up, and this red color is the all anomaly scores, which has started showing some shift in the pattern. So that has been detected, and a precautionary measure that putting this wheel into the off condition and cool off condition, and gets after 6 months make it on and operate. So that kind of insights we are able to give. This is another payload anomaly where we are able to find using this. This is another interesting part. You can see in start of the data, the red color and green color variation is same in the scale, but the density near this 16 is higher. And after 300 days, this 300 hours, this density has shifted towards the upside, that too by only 0.5 degree. If I set the limits, I will set only 19 to 15, but in between this variation will not be able to capture using that limit. But here when we are putting into the deep learning models, this kind of variation within the limits also you are able to capture. So another concept I told, when I say that my, like, let us say in this state, when I say my variation should be within this limit, and if it pattern is changed, this is an anomaly. So how you are saying that this is an anomaly, and how you will explain to the designer or the higher management that this state is not expected. So what we are doing is this architecture, we have put all the states whatever is possible in the satellites. For that, what is the expected area based on the data that has been generated and stored for the years together, the throughout the mission life. and based on those database we are able to find out and tell that yes, this was the earlier pattern and now this is the pattern, so there is a deviation. So this is kind of architecture also is very important in this our mission. This is another anomaly detections. This is another case. You can see the green is the nominal one, but there is a in between one spike which is coming, that is started getting noticed by this anomaly generator, and later what happened, the sensor got failed also. So that was one indication in months before time. This is another interesting example. This is happened in our recent very new satellite in Aditya L1, where we have magnetic suspended wheel. There what we started seeing is the range of the wheel variation is plus minus 6,000, but in between there was a change of some 50 rpm, which if you set the limit plus minus 6,000 is not at all detectable. But here, because we have trained in the pattern, this change, this short duration pattern change also we are able to notice and take the corrective actions. So these are the important. This is same plot. If you see the limits from 1,000 to 6,000, you cannot see any variation in these plots. You can see this small kink is having, this small kink is nothing but this change which has been detected. And then yeah, this is another same thing for, this is our overall dashboard which has been put in the mission operation area where people can interact and give multiple outputs. So these are the time series anomaly detection part. Coming to the interaction part, so what we have done is here, like smart operation, what we are telling that you need not to go and type something. You can, something is there, you can type, you can talk, you can discuss that this kind of problem, if it happens in any other satellite, what to do, what is the problem in the satellite, is this parameter, particular parameter is nominal, not nominal. So you can talk to the system and you can get the output. So here you can see this is all the kinds of input people are talking to the system. This system is having, you can type also, you can talk also. So based on that, it will populate, it will generate, it will send the information to the background server where architecture is sitting and all the data accessible. And then based on that, it will generate the output. Either it may be report, or it may be graph, it may be anything, plots, or it may be an voice instruction itself. So this is the overall architecture, how it is implemented. This is having three kinds of input. One is you just type and do, you run your program and get the output directly. Or you type that I want this. So this goes into the text, then from there converted using NLP model, mapped, and then again generated the data, and it is being given in the report format to the user. Or you can talk to the system, you can talk, and then text, speech to text, it will get converted, and again it goes to the pipeline and generates data and gives those. This is the interface which is very time saving for the user when he is not clear that what to do or how to find out that this particular parameter behavior is okay, not okay, or 1 year before this parameter pattern was there in this season, on this particular day in 2023 this pattern was there. So those kind of information, it can be extracted within fraction of time and immediately without putting much effort, even in real time, for decision making. So this structure is like you just open, talk, sounds gets converted, again you get the output in the plot format. So this can be plot if you are asking, if you are asking for some report or insights, it generates the insights. So how it is implemented is, it has been taken the pre-trained model, llama models, and then we have trained over our documents, our procedures, the old data which has been taken, some anomalous cases which has been generated earlier. So those things also has been trained. And then we have why we have taken llama 3. This is all efficiency which has been compared multiple models, and finally which model we have got and we have implemented. And which approach, when we are going for fine tuning of this open source model, there are so many things available which you can take it for retraining. So finally we have gone with LoRa, which is kind of you can just take the models based on your minimum requirement, you just retrain it and provide the information, and you can start using. In our satellite domain, if you see, when you are taking the pre-trained transformer, there is two very important, one is this question answering, and one is this NER, named entity recognition. Because when I'm talking about, let us say, solar current generation, this is a name, it can be indicated as an entity. So this kind of training categorization of data is being done, and then finally this models has been trained for our own purpose. And this is the overall architecture where we are getting the all the inputs from the satellite data, which can be even time analysis, frequency analysis, or time frequency mix analysis. So this is the background program which is available, which has access of the data. Once somebody gives the input that yes, I want this kind particular information, what is the variation of solar array current for this season, so this NLP based model, it converts into the instruction which is understandable by the background program. It accesses the data, it generates the data, it analyzes the data, and then provides the output to the user. So that output again, it goes to the code conversion. It can convert as a command code, or it can convert as a plot, or it can convert as a instructions. This is another same image in a large format. So you type here something whatever you want, it gets converted into parameter identification and gets converted into the time, which time to which time you have asked. This will be also displayed if, since it is in starting phase, so we have given user that if some instruction is not able to understand, so you can change manually here and it will go into our training database. So next time when we are training, so again, this kind of inputs where we have failed, where we have not able to generate the proper outputs, we are retraining the model again and again putting into the loop. So this is that architecture. I'll just show you how it is being done. This is another inputs which is coming. So yeah, this is the architecture which we have demonstrated as of now at the ground, and now we are proposing in upcoming Gaganyaan mission to be put into the onboard. What blue color things you are seeing, this is running at the control center, and the top white color boxes, whatever you are seeing, these boxes, this is proposed for onboard system. So what here we are doing as of now is we are taking the telemetry data, we are training with the historical available data, then we are testing with the designer, putting into the designer into the loop, that whatever test cases is trying to generate, his this model is able to reply to the test cases, and based on that we are again retraining the model. And this is a lifelong training mechanism has been implemented here, which always keeps on training the model. And this evaluation, once the some particular model has been evaluated and told that yes, it is performing well in these conditions, these weights are getting extracted from that model, and that weight matrix is getting uplinked onboard, so that these onboard models are also working in the proper fashion. So once the model has been trained and it has been put into the database and put into the operational area, this has been evaluated parallelly at the ground, and send the model weights to the onboard, where three kinds of model we are as of now we are emphasizing. One is voice assistant for our astronauts, other one is health monitoring of the astronauts, and third one is the telemetry monitoring. So this is telemetry monitoring chain, and this is audio video data training. This is another kind of data which is available in Gaganyaan, that we have video camera on board. The activity of astronauts or activity are the visual representation of the full Gaganyaan capsule, which what is happening inside is available as a video stream. So we are training model on that also, and that which is also being trained at the ground. As of now, we are not having any interface to train for the astronaut health, so that part is not shown here, so that will be coming into the future. So these models are getting uploaded on board, where data is available and which is going to the model training, and whatever error is trying to indicate and trying to find out that these all the issues are coming, those issues also we are taking it back at the ground, and which is being used after verification of the experts that this is valid case, and this has been again retrained the model if any issue, any wrong detection is there. So this is our closed loop simulation at present is going on at the control center, so which will be implemented in our upcoming missions which is coming next year. Yeah, so I have reached to the end. The advantage is it is having no dependency on parametric values or distribution of data. It can do the trend analysis, knowing the unknown, which we have not expected, complete health analysis, then anomaly prediction, and the interactive mission operation management. And putting the AI model on board has a lot of advantage, because if you see the satellite in orbit of 100 minutes, only maximum hardly 10 minutes it is visible over a ground station. So taking the real time decision based on that 5 minutes data, what happened in the remaining 95 minutes in the orbit, which data is not available at the ground in real time. So what happened, you are deciding after 100 minutes what has happened. But if you put the system on board, on the go, whatever is happening immediately, the system will know, and it can tell to the astronauts or tell to the system that there is some corrective action is required, that some attention is required, and so that has to be corrected. So that is very critical as of now, taking into the human into the space and interplanetary missions, where the time delay for the signal itself varies from 5 minutes to 22 minutes for Mars mission, and around when we go for the moon, it's around 1 to 2 seconds, and when we go for hollow orbit, it's around 5 to 10 seconds. So this real time, near real time data analysis and then taking the decision is not possible when you are going for interplanetary mission. So some expert system has to be there on board to take care of all this unknown things which is going to happen, unexpected things, and provide some suggestion to the astronauts, because those astronauts are not subsystem experts. They are like they are trained people, but not up to that level of the designer, so they also need some assistant to take the corrective action. Yeah, thank you for your patience. So any questions?
Thank you, Dr. Amit. So now I would like to thank the speaker and also to ask the participant who have so many questions. Please ask to you can discuss with the speaker.
So myself is Selvi Ravindran. Can I ask a question?
Yes,
Yeah,
yes, sir.
please go ahead.
Yeah, like you had described about the thermal time series data, the thermal changes in the signal. I
Yeah.
didn't know the slide number, but how are you actually predicting those things, the thermal noise changes? And there was another slide where you said there is a spike there, and because of which it's an anomaly. A small spike can be a random noise that could be coming in. It may not always be anomaly, no, sir. It normally happens
Yeah.
even in normal electrical equipment. Will have a noise.
Yeah.
So my question is
uh,
with both.
yeah, I got your question. This is another problem, as I told in my second or third slide. Why statistical based model is not giving us the proper value? What happens is, if a statistical model, if I use, and there is some 5 random sample has come, my mean will shift. So what I will detect is normal shift in the spikes which is coming in our electrical signal. That itself is a anomaly, but that is not anomalous behavior, that is expected behavior. So that's why second term comes is the contextual. When I know what is the state of my satellites, and in the previous data I have seen, if I am in the X state, these kinds of small spikes are coming. But in the model I have trained that this spikes, it should be ignored. This is, I have declared that this spike is a normal case for me. So what happens when the actual data with the spikes goes, my model knows that yes, this spike is nominal, I should not take any action. I hope I could answer you.
Yeah, I got the spike part, but the thermal noise, because it was huge chunk of signal that was there. That in that slide,
Yes,
this slide, like, really the
yes,
thermal, it's a
yes.
continuous signal. Like,
Yeah.
how do you train your model and figure out like if there is a noise here or whatever?
Okay, I'll just open that slide. It will be better to explain. Yeah. I think my PPT is visible.
Yeah, it's appearing.
Okay, so I think this was the slide you are asking, right?
Uh, it's still not come for me, sir. So I'm not
Okay.
sure. Yeah, this is the slide. This is the slide.
Okay. So what is happening in this is, let me share it again. Yeah. So what is happening is, this is see, any particular thermal sensors, if I take for anything, this kind of high fluctuation cannot happen, right? Temperature cannot change by 4 degree, 5 degree within a second, and it can come back. So what we train is, we train on the rate of the data. how the data has varied for this upcoming sample. Is it continuously varying, or it has stuck varied and came back? Again, it has varied and came back. So the important is which parameter you train for. Is the absolute parameter which is coming in the telemetry you are training, or you are deriving some parameter from the data and then you are training? You can see the start part. If I train my model on the mean value and rate of change of my this thermal parameter, will this problem of noise will go away?
Mm,
Yes, it will go away. What will happen is these spikes are sudden change. It's not having any acceleration. It's just a spike with infinite acceleration in the next moment which has come into the system, which is automatically gets rejected when you go up to the next level derivation, up to the rate or acceleration. There it gets removed, and then comes to the mean shift. Once the noise part is removed in the filter level itself, the shift in the mean you can see very clearly,
mm.
right? So when we try, we also face this problem. So what we try to do is we always try to go to next level of the data information. What are all the information I can extract from the data? It may be acceleration, it may be rate, or it may be number of samples, depending on the parameter, which kind of parameter. If it is digital, if it is a static parameter, I can take polling of some 5 samples, 6 samples. Then I can decide. If it is an analog parameter, I can go for rate, I can go for acceleration, I can go for mean shift. So those kind of derivation we do based on the system, what kind of system we are dealing with.
Okay. So like just one last question with this. Since it's a
Yeah.
time series data, we would normally sample the data at frequency, right, sir? And then we
Yes.
will feed it to the learning model. So when you do the
Yeah.
sampling, is it like uniform sampling or non-uniform sampling that you try to do?
No, that's why I told we go for the rate. The sampling part is
Oh,
over,
rate.
right?
Oh, okay.
Yeah. So but what is
Okay.
happening is for the same system, once my data, which is onboard system, these are not having kind of GPU kind of computation. They are very
Mm.
limited resource, compute power on board. So what they do
Yes,
is
yes.
all this data comes at a subsample, means once in a 20 seconds, once in a 1 minute. Some data will come once in a once in a 5 seconds. Some will come once in a 32 seconds. But all data you have to correlate. When you try to correlate sample to sample, it is not possible here. So what we mostly try to do for analog parameter is go for the derived information.
Okay. Okay, sir. Just last one question. If I want to read more about these, like what should I read? Where should I read? Because I am doing some research regarding
I
this,
think
but
all
I
this
couldn't get much.
yeah. No, I think all these outcomes we have published in the paper. And if you want to know more information, you can directly connect to our centers. People will be happy to provide you.
Okay.
And as I told, there is one program is going on called Respond. This is especially for academia only to participate in the research activity in space domain from the ISRO side, which is getting published in the month of January or February every year. And some problem cases will be mentioned. You can apply for that, and you can ask for sample data to participate into those kind of problem solving competitions, and then you can get all these informations.
Okay. Thank you, sir. Thank you. It was very informative.
Sir, good evening. This is Hemashri. I'm
Yes, ma'am.
from Coimbatore, sir. Sir, initially you spoke about the anomalies that you would identify in these telemetry data analysis. So, in real time, what kind of anomalies do we find in these kind of data? So, just to know about this.
Okay. Okay, anomaly is, in a broader term, if we say any deviation which we see from the normal, we call as a anomaly. But what happens is the small observations, if you see in analog parameters in day to day, every time it keeps happening only. So what we try to do is there any system is going to fail? Or is there any system which is not going to meet the mission requirement? So up to that level only we try to bifurcate the anomalies and object. So we call it two things. One, observation, that there is a deviation. Second, we call as anomaly, that this deviation has caused some failure or caused some inefficiency on board to perform the mission objective.
Okay, but then I thought it would be some kind of attack that would that could come into the picture there. Is there a possibility of that, or are the systems in ISRO highly secure?
I don't think I can answer this question in this
Okay.
platform, but
Okay.
anything is secured in this world is prone for the attack, right?
Yes, because my
It
area
gives
of research
people,
is
it gives people one
cybersecurity.
intuition that this system has been secured, means there is something I should attack.
Okay.
So,
Because
yeah,
I was inquisitive about this because I specialize in cybersecurity. So when we come across the anomalies, I thought there might be some kind of attack that you
so
must be
I will
tackling.
try. I'll only tell one statement. Nobody in this world is untouched by this kind of activity.
Okay, sir. Okay.
Everybody is facing that.
Okay. Sure, sir. And as you spoke about this Respond program, I would probably be interested to participate in that. Let
Yeah.
me see if we can follow up on that.
Sure, sure. It is always published. You can, there is
Yeah.
one CBPO office in our ISRO headquarters. They are coordinating. You can search online that Respond Basket 2024, 2023, and 2025 will be coming in maybe February or January end. So you can please.
Okay, I work in the area of remote sensing image classification, sir. Like, and the kind of attacks, the adversarial attacks that are possible in those kind of remote sensing data. Is there a scope for this kind of work in ISRO, sir?
Yeah, yeah. You are talking about geoinformatics, right?
Yes, yes, sir.
I'm not wrong. Yeah, that we already recently we had one challenge also across the national level to participate for the academia to find some interested area in our data which has been collected by our Cartosat series and ResourceSat series kind of satellite. So there is a center in Hyderabad called National Remote Sensing Center. So
Okay.
those people are specialized in this geoinformatics, and there is a website called Bhuvan, 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 which is
Okay.
available online where you can get all this data free of cost at any point of time. You can download up to
Oh,
5 meter resolution, and I think up to 3 meter resolution, sub-meter resolution. If you want, you can put a request to the NRSC center that all contact points are mentioned. You can get the data and you can utilize it.
oh,
It's open
okay.
for all.
Okay. I have been working on the datasets that are available freely online, like the Eurosat and the UCMUS dataset. I just
You
wanted
can
to
go
work
to you can
the
go to
real-time
Google
data.
website. All ISRO satellite data is available there. It's all
Oh,
free of cost.
okay, okay.
You can just apply it through your official emails, through your institution, and you get
Sure.
whatever you want.
Sure, sure, sir, sure.
Yeah.
Thank you. Thank you very much for the information.
Okay, there is some question from JCV. It is possible to work with the mission critical system. Can we take risk with AI and all? Yeah. Okay, so this is very interesting question. See, yeah, mission critical, but even human is not 100% true always, right? Whatever decision you are taking from some of the data insights which you have sometimes incurred or sometimes you would have seen. Yes, AI is also not 100% true, but if I take the average efficiency of 50% also, it indicates that where I should focus on. So best after the further after decision is based on the person who is sitting in front of the console. It is not that AI is going to take the decision. Is giving you the inference that this is what I have got. Now it's your turn to take the call.
Hello. So good evening, sir.
Good evening.
Uh, Sir, as you said, in this domain, so can you please describe some of the problems or that is objectives to be resolved by using LLM? Scope of
Yeah, yeah,
LLM in this.
yeah, yeah, yeah. I mean, I think I covered in my presentation, so I'll just reiterate it. Like
Okay.
any satellite, if we take, we have almost around 10 to 11 different subsystem, and each subsystem has around 1000 2000 parameters. Now let us say one parameter of one particular system X has deviated. Now I know it has deviated. What action I should to do? That action is also mentioned in the multiple document. It may be operation manual, it may be mission document, it may be flight control procedure, it may be contingency recovery procedure. And I have total window of only 5 to 10 minutes to decide and take the action. Is it possible for a human being to search for a 5 documents for a particular parameter, what action he has to take? and take the
It's
action
very
within
tough.
the time window. Is it
Yeah.
almost impossible task? But
Yes, sir.
where this chatbot comes to the loop, if you ask the question, he will be able to tell you within time, right?
Yes, yes,
That
yes.
is where is the potential is.
Okay. But since this is a sensitive area, how come we can rely on the results which are being produced by the LLMs, right?
Exactly. That's why
That's a,
there are, just before this I answered, LLM is
yeah,
not
yeah.
deciding, it's giving you the inference.
Okay.
I told there are 5 documents in that this parameter where it is described, LLM or chatbot can tell in this reference, this data, this action is mentioned. Now,
Yes, yes.
as a controller who is sitting in front of the console, he knows where he has to pinpoint. If he doesn't believe, where he can pinpoint, okay, this is the information, I should take it. I should not search
Okay.
for 5 documents, right? So what he
Yes.
has done, he has reduced my 95% of the work.
Okay.
It has not made my work zero. So
Yes, yes, yes.
people are not going to be jobless.
Yes, sir. Yes,
Yes,
sir.
they are going to be more efficient.
Exactly. Yes, sir. Thank you, sir.
Sir, I have a question.
Yes,
I mean, you are evaluating a models, and also the testing process is an infinite one. I mean, it's a lifelong process.
yeah.
In that, you are in that particular slide, you have mentioned that weight matrices has been kept away or it is extracted from the model that is trained. Why that weight matrix is kept away, or it is stored, or it is taken as a reference for the future? Or I don't understand that part. I mean, why it is
Okay,
extracted?
okay. I think it got into the complex way. The extraction is happening because those weights I have to update in onboard satellite also. Same model which is running at the ground is running at the onboard, but I got some information extra on the ground. I retrained the model how to update the onboard system.
Okay.
I cannot full model, full libraries, I cannot upload again and again. So what I do, extract the weights, that weight only you transfer. Finally,
Okay.
a trained model is nothing but a combination of weights, right?
Okay.
If I am able to update the only rate, I mean only the weights of the model, then I'm done with the new model.
Okay.
So that's
Okay.
why we try to reduce that minimum uplink requirement.
Okay. So,
Yeah.
on all the successful models, or on all the models, I mean, or on the weight matrix, do we have a version control? I mean, version control is maintained on all the, I mean, correlation, version control, and
That is the basic requirement of any software, right? So
yes.
yeah, we have all those preliminary requirement in the place.
Okay. So, okay. Thank you, sir.
Thank you.
Sir,
Yeah.
so in the transformer architecture, how does the interplay between the encoder's self-attention mechanism and the decoder's cross-attention mechanism ensure the effective alignment between the input and output sequences? How do we estimate that? Mainly in machine translation, how do we do that?
Okay. I think uh, how to explain it. Let us assume
Yes, sir.
if you want to train some particular encoder, or let us say you want to specifically wants to focus to one particular parameter when you are going for attention model.
Mm.
How do you do in the nominal case? Let us say you have one time series data. I'm not talking about text data. In time series data, how do you choose that this particular parameter only your attention should go, all other parameters should be ignored? Am I audible?
Yes, sir.
So how do you do? Can you tell me? Then I'll let you know how we do in the cross correlation. Okay.
Maybe we can do some statistical analysis on it.
No, no. I mean, statistical analysis. If you do, then what model will do? Nothing. It will do, right? You are giving cooked food to the chefs. Okay, so what we do in our telemetry data is, let us say one particular parameter X, I want this only to be focused when you are trying to detect some changes into the other parameters. What we do, we take that particular parameters, we oversample it. You got the idea?
Okay.
We
Yes, sir.
oversample it at every instant where we are trying to see the changes in the dependent parameters.
Okay,
Then
sir.
what is happening is the actual parameters which is having low frequency, it automatically gets less weightage.
Okay, sir.
I don't think you got my point, but it's okay. We can discuss anytime. I can take my email ID. You can anytime you can interact. Yeah. Okay.
So just continuing with what you answered just now, like
Yeah.
oversample that alone, and the other signals are kept undersampled. Is
Yes,
it like
yes,
that?
yes.
Mm,
Exactly.
mm.
Otherwise, those sample again will overrule my what is oversampling parameters I'm going to put.
So is it okay that we train a model with two different sampling rate of signals? That is fine.
Yeah. No, this is oversampling you don't take in other ways, like one sample at T1, another sample at T2. Then what other parameters I'm doing? I'm inserting multiple bits here. No, T1 to T2, one X parameter has changed, let us say from A to B. But my state parameters between T1 to T2 has changed 100 times because state parameters are populated at the ground. It is all propagated parameters by the estimation methods. So what I do between T1 to T2, I generate 100 steps, but the original parameter for all these 100 steps retain the same value. And the third parameter which I am taking as a state parameter, it each value is keep changing. So generally you see how your deep learning model will distribute the weightage. Which parameter is continuously changing gets automatically more weightage, right?
Yeah. Mm.
So we try to
Yes.
little bit fool the system in the way that representation of data as an input.
Thanks.
Okay.
Okay, so Amitji, I think the participants uh, have all the questions, or anybody is still there, you can have a chance because time is there. So, okay, then. So, okay, we can then thank the speaker again for the nice talk and also very interactive session. And many people have asked many questions to. Hope everybody enjoy the talk. So, thank you, Amitji. So,
Thank you, sir, for giving the opportunity. And if I have not answered any question, you can mail me anytime. Anyway, Nachikesh is having my email ID. So I will try to give you some insights with the actual data. Maybe whatever I have talked, maybe I would have not explained it maybe into to the deep, but I can share you some sample data with the actual output, so you can correlate that how this oversampling, subsampling, and how the rate, how we are extracting in the analog data. So those information, if anyone is interested, we can continue further.
yeah. So, then thanks again. So okay. So we have the next session at 7:30. So
Okay.
we'll wait. We'll wait for some around 15 minutes. Then we'll be back.
Okay, Nachikesh, thank you. Then I will take leave.
Thank you, Amiji.
All
Nice,
the
nice.
best. Thank you.
Yeah. Thank you. So once again, welcome back to all the participants. For this session, we have with us Dr. Karthik Gurumoorthy as the guest speaker of the session. Before he starts his talk, let me take the privilege to introduce him. Dr. Karthik Gurumoorthy is currently serving as a principal scientist at Walmart Global Tech by Bangalore. Prior to this, he held the role of Amazon Development Center, Bangalore, GE Global Research Center, Bangalore, and HCL Technologies, Chennai. With over 14 years of industrial and academic experience, Dr. Gurumurthy has worked on a diverse range of problems across domains such as applied mathematics, so causal inference and density estimation, inventory management, statistical machine learning, operation research, optimization, recommender systems, reinforcement learning, signal processing, supply chain management, and time series analysis. He holds a PhD and MS from University of Florida, Janesville, and has an impressive research portfolio with over 35 publications in international journals and a prestigious conference, including ECML and PKD, ICML, and CVPR. These are the conferences what Dr. Gurumurthy has the publications and all. Dr. Gurumurthy has extensive experience in interviewing candidates for applied scientist positions at Amazon and Walmart. He also actively contribute to the research community as a reviewer for prominent interfaces such as ICML, AAI, KWD, and ECML and PKDT. So other than that, I have seen that Dr. Gurumurthy also very prestigious fellowship received uh, that is Airbus postdoctoral fellowship at ICTS Bangalore, that is under TIFR. With this small introduction, I hand over the session to Dr. Gurumurthy.
Hello everyone, good evening. Thanks Nachiketa for your very kind words. I hope you can hear me right clearly.
Yeah, we can hear you. Yeah.
And should I put on my video on, or that's okay?
That's okay, no problem. No problem.
Sure. So let me just share my screen.
Yeah.
Okay, it is beginning to share. Okay, so you can see my screen?
Yeah, it's visible. Yeah, only full screen you have to make.
Okay, so it's all good now?
Yeah, now it's going fine.
Yeah. Good evening, everyone. In this talk, I'll speak about a solution approach for structured instances of mixed integer linear programming, which is what MILP stands for in the field of operations research. So the idea of this talk is to identify certain kinds of problems, certain kinds of mixed integer linear programming problems, which have specific structure in it, and using those structure, how do we come up with a fast, approximate, and efficient algorithm with provable guarantee. So the talk is all about coming up with efficient algorithms for certain kinds of problems. And more than just being an academic research, I personally have encountered these kinds of problems during my work at Walmart. In Walmart, I work as a principal data scientist in the area of supply chain and replenishment. And what what was quite interesting is so these kinds of problems are quite prominent in the field of operations research. So coming up with fast algorithms to these kinds of problems really move the needle, and they make the entire system more efficient in computation. So the talk is all about how do we develop such a fast algorithm. And Nachiketa, will this talk be an interactive, or will be more like questions at the end?
In general, we are doing questions at the end. So you can keep 15 minutes, like 150 minutes you can speak, and then remaining 50 minutes we can discuss.
Sure. And if anybody wants to ask questions, please do so, because it might help to clarify certain aspects of the talk. So yeah, so please feel free. Okay. The talk is all about MILP, which stands for Mixed Integer Linear Programming, where the problem has a specific structure. So generally, mixed integer linear programming problems have two kinds of variables. The x variable, which is a continuous variable, which takes a value between 0 and 1. So these indices n, r, i, e, you can probably ignore that for time being. That they corresponds to certain kinds of variables where I might refer to an item, the n could represent some kind of a, let's say, a node, which can be a distribution center or a fulfillment center or a store, something like that. The R corresponds to some kind of a region. Think of something like a zip code. And E could correspond to some kind of an edge. The edge might be certain modes of fulfillment. For instance, if a customer from a region R is ordering an item I, which needs to be fulfilled by a fulfillment center. For example, all of us order things like Amazon or Walmart. So we order from a particular zip code which represents the region R. And let's say we order an item. The item can be, let's say, a shampoo. And we want the item to be delivered from a particular fulfillment center. We customers do not choose the fulfillment center from which these items arrive, but all retail companies would kind of want the item to be fulfilled by so-called the nearest fulfillment center. For example, if I'm situated in Bangalore, I'm ordering a shampoo, it is best for a company to fulfill the item shampoo from the fulfillment center in Bangalore or somewhere very close. That fulfillment center is what I call as N, and E could correspond to different modes of fulfillment. For example, the item can be fulfilled by a road transportation. If an item is coming up from a faraway place, let's say from Delhi, the item could actually be shipped to Bangalore by a flight and then transported to the customer doorstep through a last delivery station. The E could correspond to different kinds of fulfillment mechanism. That's what this X variable denotes. And the Y variable is actually the integer variable. So I'm looking into certain instances of mixed integer linear programming where the objective function is a function of a continuous variable X and an integer variable. By integer variable, you can only take integer values, let's say for 0 or 1. And the objective is to identify these values of X and Y, which minimizes a combination of a linear cost on X and some kind of an integral cost on Y. So these these variables like D, P, F could be certain constants in the problem structure. For example, the F could kind of denote even what kind of, for example, if you want to place an item I in a particular fulfillment center N, where yi could indicate whether item is placed or not. For example, if I'm choosing to place shampoo at the Bangalore fulfillment center, that decision could be y, and f and I. This could indicate that the cost associated with even placing an item in a fulfillment center. So this could be general. So any kind of a mixed integer linear programming which has these two kinds of variables x and y, where x is continuous and y is integer, and the objective is to identify the value of x and y, which minimizes this combination of linear cost and integral cost. I will delve into specific examples which has this property of the linear, which have this specific MILP instance. I'll explain that in the next slide, but in a general, the talk is all about coming up with fast, efficient algorithms which can satisfy this instance of MILP. And generally, such an MILP problem will have a suite of different constraints on the decision variables x and y. For instance, the x could denote some kind of a demand fulfillment constraint. That is, what portion of demand for an item I from a region R is fulfilled by the node N through a particular fulfillment channel E. So the E could be a fulfillment channel, like I said, could be either ground transportation, could be air transportation, could be even different modes of fulfillment, for example, like FedEx, or it could be like UPS in the US marketplace. So the X could denote some kind of a demand decision variable, which indicates what portion of a demand is fulfilled by these nodes are meaning that these are just certain variables there. So similarly, one could also have some kind of constraints on how much of quantity of items is stored in a particular fulfillment center. For example, one can say that the entire capacity of the Bangalore fulfillment center is about 10,000 units. And I can put among all items put together. So how much of items I'm going to store in Bangalore fulfillment center that cannot exceed 10,000 units. The 10,000 could be the value of BL, something like that. So one can have different kinds of constraints on these on the continuous variable X, and also on the integer variable Y. So the continuous variable should take a value between 0 and 1. And the integer variable should take the value 0 or 1. So any kind of such MILP problem with this notion of a linear cost and integral cost. So I'm looking at problems that have this instance, and then how do we come up with fast solution to such problems? So this problem can be shown to be NP complete, which is this problem is as such. To get the global optimal solution, it is going to take exponential number of time unless P equal to NP. The standard results in computational complexity. So if you want to take this problem and put it into a global solver, the running time to solve these problems for decision variables X and Y could be really long. So idea is to come up with fast approximate algorithms which can come up with almost near optimal solution, but at a greater computational speed. The talk is all about for coming up with such a solution design for problems of this nature. So any question here? I know that the questions are done to the end, but if anybody has any questions, please feel free to ask. So before we solve this problem, I want to kind of touch upon, I want to rephrase this problem into a specific formulation. The advantage of that particular formulation will lead to faster solution. The first thing is the problem which I mentioned here could be reframed as a subset selection problem. How? So let's define a subset S as this the combination of these indices I and N, where I, as said, could be an item, N could be some kind of a node, and the YIN could actually mean the aspect of placing this item in this node, the aspect of placing a shampoo in the Bangalore fulfillment center or not. Meaning, for example, if you choose not to place shampoo in Bangalore's fulfillment center because of space constraints, or because people in the southern part of India for some reason do not order shampoo, so it is better to place shampoo in the northern part of India. Such a decision can still be taken by the retail industry. So the question is, should I place shampoo here or not? So if we define the subset S as the set of all indices where the decision variable, the integer variable, takes the value N, then the entire problem can be represented as a set function G, where G is a set function which, given the set S, where let's say I say that these are the indices where Y takes the value 1, then the set function is nothing but a maximization function over the variable X alone, where X is a continuous variable. Given Y is given. So for every choice of Y, one can define this corresponding set S and then define this set function on the set S, which is defined as a maximization function over X, where Y is given by the set S. Then, so the transform problem is then maximize over S, the set function G, subject to constraints on S. So the same problem, MILP, is now reformulated as maximization of a set function over a set S, where the set function is defined by this equation G of S. This is nothing but a reformulation. The advantage of the reformulation is as follows. And before I come there, this problem has additional structure. What's the structure? Once the set Y or once the set S is specified, the set S is basically the indices where the integer variable Y takes the value 1. So once the set is specified, this function G of S is nothing but a linear program with maximization over X. So the linear program is critical here. So the integrality constraint, which makes the MILP problem NP hard, is now once we specify where the integer values are 1 or 0, let's say, that becomes the set S, then the set function itself is a linear program over maximization over X. Secondly, as I will discuss in the future slides, this set of linear program has a very specific instance. It can be represented as an instance of an optimal transportation problem or a capacity constrained optimal transportation problem. So these are sub-instances of linear program with more structure in it. I will describe that also. So here the linear program itself has more structure in it. That is, it is an instance of an optimal transport problem or a COT problem leading to efficient computation, where the general cubic complexity of a linear program is reduced to a linear complexity of an optimal transport problem. And I will kind of explain what optimal transport is. The structure is as such. So we need to solve a set function G, where the idea is to maximize the set function G over the set S, subject to certain constraints on S, where the set function G is a linear program. It is not only a linear program, but also a specific instance of an optimal transportation problem. And more importantly, the set function G satisfies the property of submodularity. I'll explain what I mean by submodularity. So the topic is all about solving this set maximization problem over G, where G set function satisfies the probability of submodularity. That is important. Second thing is, once the set function G itself is the instance of an optimal transport problem or a capacity constrained optimal transport problem. So such a structure, if the problem has certain structures like this, one can solve it much more efficiently rather than solving the instance of MILP directly, which we know is MP complete. So I will now describe different kinds of problems which is encountered in operational research, which surprisingly satisfies this beautiful structure. The first one is something called a multi-channel facility location problem. I will describe this in detail, but if I kind of look into the objective function of the facility location problem does have this notion of some kind of an integral cost over this variable y, some kind of a linear cost over the decision variable x, which is given by the terms 2 and 3. So this satisfies the same MILP instance which I spoke about earlier. And there is also called inventory allocation. I will also talk about this inventory allocation, which is about how do we allocate inventory from a distributional center to multiple stores. I'll describe these concepts in the future slides.
Yeah, Dr. Karthik, that one thing I just a little bit confused, that this when you say that integral cost, and that one is that this your linear cost. So what do you mean by that integral cost?
The integral
because
cost
y is integer.
Y is an integer variable.
Oh, that's why you're telling integral cost.
I'm just calling it an integral cost.
Okay.
So y is an integer variable. Yeah, that's it.
Oh, that's it. But overall, but summation is just linear combination, right?
It is linear summation. Summation is linear, except that this decision variable y is an integer variable, which is what makes the problem really hard to solve. Otherwise, the problem is a simple linear program.
No, because of that integer thing, so this is a problem.
So these are problem instances where there is some notion of an integer valued variable and a continuous valued variable. Both are linear. So both the terms are linear.
Both are fine.
So there are different kinds of problems, which is multi-channel, which is facility location, inventory allocation, inventory placement. So these are actually different problems in the operational research domain, which surprisingly has this has the specific structure. All these are standard MILP problems, mixed integer linear programming. The advantage is all these problems has the structure of the set function G happen to be submodular, and the set function G is can be written as an instance of an optimal transport or a capacity constrained optimal transport. So these are just kind of flashy. Yeah.
The submodular means what is the use of that? I mean, what exactly? I'm not able to understand. What is the
I will describe the next slide. Exactly.
Okay.
So right now, I'm just talking about a general structure. I will explain these concepts in the next slide. So here I'm talking about different problems in, tangible problems in operation research, which have this specific structure. So I will touch upon the first two problems. Inventory placement is nothing but an extension of the facility location problem. So I might not have time to touch upon inventory placement. I'll go in detail about the first two problems, and I will connect it with the submodularity and optimal transport theory, which I spoke about, and then how do we use that property to come up with efficient algorithm. So, okay. So what is a multi-channel facility location problem? So here, the idea is, okay, so assume that we have different, assume that, let's take one item, shampoo, right? And we have some notion of a demand of the shampoo across different zip codes in India. Different zip codes, we have some notion of what is the expected demand of the shampoo is. So now the question would be is, given certain kinds of, let's say even stores or even fulfillment centers or anything, the question would be is, what fulfillment centers or stores one need to place the shampoo, and what quantity of shampoo has to be placed there. That is the problem. The facility location problem is all about deciding which in what facilities, or facilities is nothing but another jargon for stores or distribution centers or any of this supply node. A store or distribution center which is going to meet the demand for a region or a customer is what I call it as a facility. So the question would be is, in what facilities out of the given list of facilities one has to even place this shampoo. So when I say place the shampoo, it is synonymous to the notion of opening the facility. Opening the facility to placing this item shampoo in it. One could ask, okay, why can't I just place the shampoo in all the facilities? The problem is the very aspect of placing an item itself incurs cost. Because once you place an item in a store, we need vendors to kind of supply the item to the store, which itself is expensive. So it is sometimes worth not to place the item in all the stores, which is not done unless the item is extremely popular. Otherwise, even the certain static decisions are even taken to kind of decide what, given an item, in what facilities or stores should one place this item. That choice is made based on where the demand occurs. Meaning, for example, if the demand for shampoo is quite heavy in the northern part of India, I would rather place shampoo in all the stores in northern part of India and not place it in the southern part. Or place it in the southern part of India at very few number of stores. That choice is what is called a facility location problem, which is given the supply chain network, which will have these facilities, customer demand locations, and different modes of fulfillment channels between the facilities and the customer demand locations. Which facilities will be recommended to place this item, so that some aspect of a variable cost which is nothing but the cost incurred in shipping the item when the customer places an order, and the fixed cost which is associated with even placing the item in the facility is kind of minimized. That's the facility location problem. So the input is like, okay, we have, let's say, so the network information which talks about the demand at different customer locations, the capacity of the facility, which facilities are connected to which demand locations, and what kind of transportations are available. Either you have ground transportation or you can have air transportation, and what is the cost of transporting this item through this different transportation network, and what is the capacity of the storage capacity of the facilities, what is the capacity for different fulfillment channels. So this is what the input, this is what a supply chain network. The question would be, is given all this supply chain network, one can kind of decide what facilities to open. So it could also be in a setup where, let's say, there are certain number of fixed facilities, let's say 10 facilities where the items are already placed, and have a list of, let's say, another 50 facilities, probable candidate facilities where the item can be placed. Out of that 50, how many, let's say, can we choose about 15 of them to be added to the existing 10. So it can be even more like something like expanding new facilities. Or it could also be used in a greenfield setup where I don't have any facilities where the item is placed. I want to decide afresh what facilities have to even carry this item. So these are just different variations of the problem. So as I said, so the problem description is, so we have facilities where the item is which is open to place this item. It can be any item. So each facility has some aspect of facility capacity, that is how much units it can hold. And we have demand locations, which can be zip codes, where demand occurs for this item, which are here marked as these human faces, right? And in certain cases, there can be places where these facilities marked as dark blue already open, meaning they can be so-called super centers, where the item is always placed. And the question would be is, okay, I have a list of these green locations, which are probable candidate facilities that the item can be placed. Given that I want to find a subset of these green facilities where the item will be placed. For instance, here, out of 1, 2, 3, 5 of these green facilities, the algorithm recommends to place it at these 3 points. And it chooses not to place on the other ones. The choice of where to place this item and where not to place this item is basically the instance of the objective function, which will depend upon the cost of meeting the particular demand for a client or for a customer location through a particular channel. Those would be the input to the network. So we'll have facility opening cost, which could be opening cost could also mean the cost of this placing the item. We have shipment cost, which leads to if customer from this customer places a item to order, how much it is going, how expensive it is for different facilities to meet this demand, 1 unit. For example, this facility is very close to this demand point, so this may be cheaper to sell it from here. But for the same demand location, so sending it from here is much expensive, or it is not even possible. Those are shipment cost. And this is more like some kind of regularizer, that is any penalty on unfulfilled demand. Meaning, because if any aspect of demand is not fulfilled, that leads to very bad customer experience. So there is some kind of penalty of an unfulfilled demand. So given this network structure, how do we decide new facilities or what facilities to add? This I said is a standard instance of MILP, but unfortunately it's NP hard and doesn't scale. So this problem, we can formulate it as a subset selection problem and use the property of submodularity and optimal transport theory to come up with efficient solution. So I spoke a lot about submodularity, optimal transport theory. I'll just explain what it is. So submodularity is a property of a set function where the addition of a single element, when added to a input set, that is the value of adding the single element added to an input set decreases as the size of the input set increases. In a simple example, assume that I like to have a cup of coffee. If the first cup of coffee, when I have it, it gives me much better kick, meaning I feel excited. So now, when so excitement is more like the value. The coffee, the cup of coffee is more the single element. When I have had no coffee, meaning that is when the set is empty, having the first cup of coffee gives me much more excitement. Now, if I already had, let's say, 5 cups of coffee in the day, right? The set contains 5 elements. Now, if I had the same cup, if the same cup of coffee is added as the 6th element, the excitement that it is going to create is lesser. That is exactly what submodularity means. So, if we add a single element, in this case, let's say there is 2 network of facilities already available. The network S1, network S2. Note that S2 has more number of facilities. There are 4 facilities in S2, and there are only 3 facilities in S1. Think of S1 as I already had 3 cups of coffee, and S2 I already had 4 cups of coffee. Now this new F is another cup of coffee I'm going to add. The amount of value it has, value is determined using this difference. That is the function, set function G operated on the union, S1 union F, minus the same set function operated on S1, which is like the total 4 cups of coffee minus the excitement I had with 3 cups of coffee, which is what this is, the incremental value. That incremental value for adding F to a smaller subset is greater than adding the same F to a larger superset S2. That is, the 4th cup of coffee added over 3 cups of coffee gives more excitement compared to adding the 5th coffee over 4 cups of coffee. Same thing. So that whenever you add a new element to this set, the incremental gain or value that it has is the same set F, a same new element F added to a smaller subset is more valuable than adding the same element F to a larger superset. Any set function that satisfies such a diminishing returns property is called a submodular function. Right? So why the submodularity? I'll come to that. This is what at essence submodularity is all about, diminishing returns. So the optimal transport theory, which is another well-studied field, is all about coming up with optimal allocation between a supply node and a demand node. For instance, assume that the supplier nodes are supply 1, 2, 3, and this supply has some kind of a capacity, which is, let's say the supplier 1 can only meet 100 units, which is what supply capacity S1 is. Supplier 2 can meet 200 units, which is capacity S2. And we have different demand locations, which have the maximum demand that a particular location can take. Let's say customer 1 is location 1, customer 2 is location 2, etc. Each of these columns has some notion of a demand constraint, a D1, D2, D3, D4. And between every supplier and customer pair, there is some notion of a profit per unit of fulfillment. That is, if supplier 1 is meeting 1 unit of demand per customer 1, then the profit is, let's say, 10. The supplier 1 is meeting 1 unit of demand for customer 3, the profit is 5, which is what this Pij is. The optimal transport theory is a specific instance of a linear program where the objective is to identify what portion of demand is met by between a supplier and a customer pair. That is, given this is a supply constraint and the demand for different location, we want to see whether supplier 1 meets 10 units of 10% of demand for customer 1, 20% of demand for customer 2, etc. The 10, 20, 30% is what we are solving for, which is the Xij variable. The objective is to maximize this profit subject to the supply constraint S and the demand constraint D. So the linear program with this instance is called an optimal transportation problem. It's all about what is the best way to transport items from a supplier point to a demand location, so that transportation leads to some aspect of profit maximization or equivalently cost minimization. Right? So this is what optimal transport problem is. So given this very brief introduction, I'll talk about how these two properties it can be leveraged into the certain instances of MILP which I spoke about. Right? So to see, for example, let's consider the facility location problem. As I said, right, the problem is to identify certain portions of the certain subsets of facilities which needs to carry this, let's say, item shampoo, so that some aspect of cost is minimized. Right? The same problem can be represented as a maximization problem over the set S. So this is again some kind of a transformation where the minimization problem J can be represented as a maximization problem over a different set function F. So this transformation is not hard to see, but I'm not going into the details of it. Take it for granted that it can be done, where this minimization problem can be rewritten as a maximization problem of an equivalent certain transformed set function F, where this set function F is actually a set difference, is actually a difference between two set functions G and H. Okay, where G becomes the set function H is just nothing but the cost of opening the facility of the facilities in the set S. That is, the set S corresponds to set of all facilities, right? Which is what
you mean the maximization is it a dual based thing or a maximization minimization contrast?
It can be thought as some kind of a dual equivalent to it.
Okay.
But it is more like a reformulation.
Okay, fine.
Right? So this H is nothing but the cost of opening all the facilities I in the set S, which we call as a modular function, which is like modularity basically means it is stronger than submodularity, where the cost of where the value of adding an item, new item to the set, that value remains constant independent of the size of the set. That's called a modular function. Here it is just linear. So H is this something called a modular function, and G is the maximum profit demand allocation function. Okay, so basically what I'm saying is this is the objective for the multi-channel facility location. This is a minimization problem over the set S, which is what we want to solve. The same thing can be re-represented as a maximization problem over the difference of two set functions G and H, where G is maximum profit demand allocation problem, and H is nothing but which is the sum of all cost of opening the facility. That's it. So now, given this, what is actually can be proven is the G satisfies this property of submodularity, which is what we will leverage to come up with faster solution approach. So the F is represented as a difference between two functions G and H. G satisfies this notion of submodularity, and H can be proven to something called a modular function. For such a structure, in ICML, Harsha and et al. Came up with a greedy provable algorithm. And we will leverage that algorithm to come up with a faster approximate solution. So the facility location problem can be transformed into a problem where we want to maximize the function set function f for the set S, where f as is represented as the difference between set function g and h. G satisfies the property of submodularity. H satisfies the property of modularity. Whenever to maximizing such a function, as a simple greedy based algorithm is developed by Arshan et al., which can come up with efficient algorithm to maximize the function f. The algorithm is actually straightforward, which is you start with some kind of an empty set S. Okay, then for all facilities E, solve for the set function g of S union E. When I say g is this one. That is, whenever S is specified, the g of the set function is obtained as a maximization problem over the continuous decision variable x. Here, g is the linear program, which I mentioned in this earlier slide. Okay, which is what I'll talk about is the g can be solved efficiently. So g is the linear program. Okay, solve this demand allocation problem g. Find the incremental gain, meaning how much of adding this facility E, what is the value, which is the incremental gain, and G being a submodular function, this incremental gain has a diminishing returns property. And to this incremental gain, they apply some kind of a distortion factor. The distortion factor is not very intuitive, or it is the distortion factor is basically applied to come up with some kind of provable guarantees. So I'm not going there. Assume that some kind of distortion factor is applied to it. So what they then say is, among all this new facility, choose that facility E star which leads to the highest distorted incremental gain. Right? Compute this, you iterate this for every possible facility E, and choose that facility E which has the highest distorted incremental gain, and add that E star to S, and repeat the process. This is the algorithm. So it's actually very, very simple. It's like start with an empty set, choose the element, you choose the facility which when added to the set leads to highest distorted incremental gain, and then repeat the process. That's it. Right? So that is, in this case, if we start with an empty facility, choose the facility which is open, or where when you place an item leads to best profitable demand allocation, then choose that facility. Now let me call it facility 1. Given that shampoo is going to be placed in facility 1, which is the second best facility I need to add to facility 1? Assume that facility 1 is the store in Bangalore. The facility 2 could be either Chennai or Hyderabad. I want to choose one to be added alongside Bangalore. Assume that it is Chennai. Given that Bangalore and Chennai are open, which is the next store or city I want to add? It could be either Hyderabad or Delhi. Just repeat this process. This will lead to optimal selection of facilities. This is the algorithm. The real complexity is the algorithm does not tell us how to efficiently solve this demand allocation problem G. Note that G is itself a linear program. Okay? Repeatedly solving the linear program is very, very expensive. But the algorithm developed by Arsha et al., for them, they assume that solving G is something called an oracle, which is like they don't care about the complexity of solving G. You give a set S, you have an oracle or some kind of mechanism which will give you the value G of S. They don't talk about the complexity involved in solving G. In our case, G itself is a linear program. So repeated solution to G itself is very expensive. So the question is, how do we efficiently solve this demand allocation, a linear instance, quickly? Because if this is solved efficiently, the other framework is very simple, which is basically what we want to follow here. The problem is, for every iteration S, we need to solve the demand allocation for every possible candidate facility E. So let's say if I want to choose 50 facilities, okay, and there are about 1,000 facilities which I can start with, I would start with 1,000 in the first iteration. Second, from the 1,000, I would choose one. Keeping that one fixed, I would again try with all the remaining 999. So from there, I will choose one. Keeping 1 and 2 fixed, the third iteration, I have to solve over 998. So this is expensive. This is like order n square, where n is the number of facilities available. And solving order n square instances of linear program, where each linear instance is cubic complexity, is very expensive. The question is, how do we solve the demand allocation problem much more efficiently? Here is where one can leverage the concept of optimal transport theory. Right? Okay. So the optimal transport theory generally deals with, as I said, supplier. So optimal transport theory deals with, given a supplier and a demand, what is the best way to allocate to meet the demand by a supplier to a particular demand location. This optimal transport theory has no notion of different modes of fulfillment channels, meaning that concept doesn't exist in optimal transport theory. It's all about, okay, I have a supplier, I have a demand, okay, I have different customers at different demand locations. What portion of the demand has to be met by what supplier? It doesn't have a notion of how the supply itself can be met. That is, the different fulfillment channels. For instance, either via ground transportation, via air, via two-day air, something like that. They are called different fulfillment channels. So this concept doesn't exist in optimal transport theory. Then the question would be, how do we adapt the optimal transport theory setup for our multi-channel facility location problem, where the same supplier could fulfill to meet the demand for the same customer by different mechanisms or different fulfillment channels. So to solve this multi-channel problem, we can adapt something called a multi-stage optimal transport theory. When I say multi-stage, here it all works. Assume that there is one facility and a client, and these three red and the different colors are different fulfillment channels. Where red can be ground transportation, blue can be one-day air shipment, the green can be two-day air shipment. So there are the same facility one can meet the demand for client one via different mechanisms. What we do is, in the multi-stage optimal transport, in the first stage, we create an abstract channel between a facility and a client, which is this dotted line, by combining these three channels together. So we merge multiple fulfillment channels into a single abstract channel, and for this channel, we introduce some notion of profit of fulfillment, nothing but which is the negative of the cost. So some aspect of, okay, if I use an abstract channel, what is the profit that we achieve if the facility one is meeting the demand of client one? So there are different mechanisms in which this profit can be defined for the abstract channel. Right? That's again problem specific to some extent. So once we do it, so now this reduces to an instance of optimal transport, where I have facilities and there is only one channel between a facility and a client. So in stage one, we transform. So in stage one, we just treat it as a problem between facilities and clients, where For each facility, we have the facility capacity, and each client points, we have the corresponding demand, and then we have this profit for a facility and a client location. This is a simple optimal transport problem. Optimal transport problem can be solved in almost linear time. An approximate solution to optimal transport can be achieved in linear time, which was what shown by using a methodology called synchron distances. I mean, I don't have time to go to synchron distances, but it was shown by Kiteri in the newspaper 2013, where he showed for optimal transport problems how some notion of entropy regularization can be employed, for which good quality approximate solutions can be obtained in linear time, reducing the cubic complexity of LP problems into a linear complexity. The same thing can be leveraged here, where so now in stage 1 we have transformed to an instance of an optimal transport problem. So we solve stage 1. From stage 1, what we get is what portion of demand for a client location is met by a particular facility. So once we get stage 1, we are not completely done, because we also need to identify what portion of the demand is satisfied by each of the different channels, meeting their respective channel capacity. That is where stage 2 is. So once we obtain stage 1, which says that, okay, facility 1 is going to meet 10% of the demand for client 1. Facility 1 is going to meet 20% for client 2, 30% for client 3, etc. Right? Then we want to then say, okay, if I say 10% for client 1, the 10% is met by what percentage are met by individual channels. That is, out of 10%, 5% is met by channel 1, 3% is met by channel 2, 2% is met by channel 3. We need to still solve that thing. That is where the stage 2 comes in, where again in stage 2, for each facility, the stage 2 can again be represented as an optimal transport problem, where the row, each column constraint would correspond to what portion of demand is met by the facility to different client location, and different row constraints will be the channel capacity for that particular channel. Right? So by solving stage 2, we'll be able to also obtain the optimal distribution of the demand to even to individual channels. The stage 2 can be solved independently for each of the facilities and in parallel. So long story short, so this linear instance, which is nothing but again an instance with this linear program, which is the demand allocation between a facility I, a client J, and a fulfillment channel E, can be solved as in 2 stages, as 2 stages of optimal instance of optimal transport. The advantage is optimal transport can be solved in linear time compared to the cubic complexity of the linear program. That leads to efficient solution. So once the set S is given, that linear instance is solved as a multi-stage optimal transportation instances. Where in stage 1, we merge these channels to form an abstract fulfillment channel, and we determine what portion of client demand is met by what facility. And stage 2, we then again represented as an instance of an optimal transport problem, where we further compute what percentage of the demand is met by each of the channels. So the multi-channel facility location problem is solved as a multi-stage optimal transport problem. So both stages are again instances of optimal transport. They are instances of optimal transport, and else can be solved efficiently using some aspect of entropic regularization. Right? So that's how, so basically we are able to solve this linear instance efficiently every time, and hence the overall solution would again be much faster. Right? So, okay, so this is the solution approach. The other advantage of our algorithm design is the facilities are added incrementally one after the other. So this notion of adding facility incrementally can be also used to kind of rank the facilities, where a facility of rank 1 basically means it is the first facility that is added from this entire set. A facility rank 2 means the second facility that is added. The rank of the facility corresponds to the incremental benefit of adding a facility, given the fact that better ranked facilities are already there in the set. Okay, so this rank as notion of what is the value added by a facility to my subset selection problem. This notion of incremental benefit is much more useful to a solution designer rather than some standard notion like say like facility capacity. So generally people think, okay, a facility's higher capacity needs to be included, but that's generally not the case. For instance, the diagram here, what I plot is, I rank in the y-axis, I plot the rank of the facilities, and the x-axis, I plot again the rank of the facilities as per facility capacity. The y-axis is the rank here indicates when the facility is added to my set, meaning the first time a facility is added that becomes rank 1, the second facility that is added is rank 2, etc. The x-axis, it is now ranked based on facility capacity. That is the most facility with higher capacity comes as rank 1 in the x-axis. All points above this dotted line are those facilities which are, even though they have higher capacity, they are not included earlier. Meaning these facilities do not have higher benefit of being added to the solution. So this fictitious notion of using higher capacity is questionable, and it's generally not the case. Even the facility has higher capacity, it might not add value in terms of minimizing the shipment cost when being added. So that's where the ranking based on incremental gain is much more beneficial to any kind of retail business. And the other advantage of this rank is assume that an experimenter who's deciding this facility wants to is not still decided about how many facilities to open. For example, should I need to place this item shampoo in 20 stores or 30 stores or 40 stores? Nobody gives the number 20, 30 or 40. If you want to run MILP, which is standard mixed integer linear programming solver, we need to solve the instance for every value of 20, 30 or 40 because we do not know yet. In many cases, we will not know because these are just design choices. But that is quite expensive. But in our case, since the facilities are added incrementally, so one has a flexibility to kind of decide when to stop adding a new facility. So that choice can be made by this notion of incremental gain. That is, if I add a new facility and the gain for adding a facility is very minimal, I can pretty well stop there. The stopping point could be, let's say, after adding 25th facility, or it could be even after adding, let's say, the 35th facility. The choice is given, one can make an informed choice of when to stop adding new facilities to my set, instead of rerunning the algorithm for every value of the choice, which is quite expensive. So that gives much more flexibility in designing it. So to kind of compare our solution approach, I basically compare 3 different methods. The method 1 is solving the MILP as an instance of MILP using state-of-the-art commercial solver, which is method 1. The method 2 is we follow the incremental notion of adding the facility, but the set function G is solved directly as an LP, which is, as I said, okay, so this is an incremental solution, but in method 2, this G is directly solved as an instance of a linear program without solving it as a multi-stage optimal transport problem. So that method 2 is where this G is directly solved as an LP instance and solved using commercial LP solver. Okay, that is method 2. The method 3 is a proposed method where the linear instance itself is solved as a multi-stage optimal transport problem. So what I plot here is for different, the x-axis I plot the number of facilities to open, whether 10, 20 or 70. And the y-axis I plot the running time in logarithmic scale. You see that there is a huge difference in the time taken by these 3 methods. So the MILP takes humongous time to complete, and we actually ran it on the proper Walmart scale problem, and for certain large size network, the MILP actually ran for days and it didn't finish. We had problem of that scale, which is natural because MILP is an NP-hard problem. It takes exponential time to actually solve. So directly solving it as an MILP is going to be time consuming. And the method 2 is the linear, where is basically where the linear program is solved as it is. It is still expensive. And the method 3 is green, is where we solve the same LP instance as a multi-stage optimal transport problem. The method 3 is literally 100 times faster and is definitely scalable. The question would be is, okay, do we achieve this computational speed for lack of optimality? The question is actually no. So the solution that we obtained from our method 3 is within 3% of the optimal solution of the commercial solver. So the solution gap, optimality gap, is pretty minimal experimentally. And even the facilities that were chosen, there was more than 80% lap between the facilities chosen by a method 3 compared to using the commercial solver. So we don't even forego on the optimality of the solution. And that's what this actually talks about, the relative difference in the objective function value. Then the difference in objective function value was within less than barely 2% for most of different number of facilities to open. And here we plot about, we discuss about even the intersection of actual facilities that were chosen by different solvers, where the intersection is about 80%. To kind of summarize, so we developed a solution approach which is fast, which adapts well to large-scale complexity. We're able to recommend facilities to even open or even close. It can be extended even to cases where we want to close down certain facilities, that is facilities where we don't want to, let's say, carry this item. And it ranks the facilities. The ranking has a higher advantage in coming up with faster experimental design. And we are able to achieve the solution in a fraction of computational time and resources compared to commercial solvers. Right? So this is like one aspect of the solution. So I'll quickly touch upon a related problem, which is inventory allocation, where this similar structure also holds. So I'll just keep this brief as we're running out of time. So inventory allocation is identifying how items have to be allocated between, let's say, a distribution store a distribution center to multiple stores. When I say distribution center, it is more like, think of a warehouse. And the stores are actual physical stores. Let's say we have a setup where there are about 20 stores, physical stores, and each store is requesting about 20 units of shampoo. The demand, each store is saying, okay, I need 20 units of shampoo to be physically transported to me. The warehouse caters to all the 20 stores. Okay, so there are 20 stores, each store is demanding, let's say, 10 units. The total requirement is 200 units of shampoo. But the warehouse has only about 100 units with it. How do I distribute these 100 units to the stores? Right? That is an allocation plan. So whether should I take this 100 and distribute equally to all the stores, which basically means there are 20 stores, each store only gets 5. Or should I do some kind of a different allocation depending upon factors, let's say like a popularity of a store. For example, if a store is newly opened, right, that store is going to attract more crowd. So maybe for that thing, we want to ensure that that store gets all the demand because it's a new store. There is going to be higher footfall. So we need to have some kind of mechanism to kind of decide how inventory from a warehouse gets allocated to different stores. Okay, that is a inventory allocation problem. And secondly, the inventory allocation problem also has some notion of trailer capacity. The instance that assume there are about 10,000 items, and each store is requesting different quantities of each of these items. Okay, and all the items are placed in this warehouse, which needs to create an allocation plan for every item, every store. Right? Now, these items have to be physically transported to a store using a tractor trailer. Okay, so these tractor trailers have some aspect of a capacity. They have a maximum capacity, which is how many units that a tractor trailer can actually hold. Interestingly, they also have some notion of a minimum capacity. That is, how many units this tractor trailer should at least be loaded. In many cases, this happens in reality where if a tractor trailer is not loaded up to a minimal capacity, the trailer does not move from the warehouse. It just stationed there till it gets filled. So even though if we allocate certain units of different items to a store, if the tractor trailer to the store is not filled up to a minimum capacity, allocating those units to that store is practically useless because the tractor trailer is not going to move. It is still going to be there. And as long as unless more units are added, it will just stay put at the warehouse. This makes the problem much more interesting in kind of deciding what quantities of items have to be allocated to what store. Right? This is the inventory allocation problem. So it is about each forecast. So there is a forecast engine which predicts what is the demand for each item in the store for multiple days in the future. Right? And there is a plethora of business constraints, and the inventory allocation system then decides, given all the input and the demand constraints, how much of items have to be allocated to each store. Okay, I'll just touch upon few concepts here. For the forecasting model predicts for each item store combination of multiple days into the future, what is the expected demand of this item in the store. Okay, so right now, what happens is this inventory, based on inventory availability at the store, typically a rule-based system is generally deployed, which kind of comes up with this allocation plan, which says that, okay, given this, that for shampoo, there are 200 units of shampoo at the warehouse. Paper towels, there are 1,000 units. Let's say some other product, there are about 10,000 units. These are the inventory availability for this item in the warehouse. These are the demand for the store item, different stores and different items. how do I allocate this item to the store is the inventory allocation plan. They're dispatched using trailers. However, this rule-based system generally is, it only looks into inventory, but it does not look into some aspect of labor, which is, what is the human availability at the warehouse even to process this inventory allocation. For instance, on a particular day, if a warehouse has only about 10 people working there, the 10 people can only process 10,000 units of product. So whatever inventory allocation is done across all stores and items, the total inventory allocation cannot exceed more than 10,000. On weekends, the number of people working there might be more. So this is nothing but this is known as the labor capacity, which has to be incorporated even deciding the allocation plan. Similarly, the allocation plan should also factor in trailer capacity, which I said. Certainly, if the trailer is not even filled up to a minimum lower bound, the trailer is not going to move. So a system which looks into each aspect in a parochial sense will lead to sometimes even infeasible solution. So the objective here is to then come up with a holistic approach which can optimally design an inventory allocation plan. Right? I think we are there's 5 minutes here. So I'll okay. So the objective of this InVals is it's a new forward-looking inventory allocation system. When I say forward-looking, what it does is it doesn't only look into the immediate store demand. That is, it doesn't look into, for instance, today's store demand. Today, the store might need 20 units of shampoo, right? And if we allocate only 20 units of shampoo, it might lead to the setup where I don't hit the minimum trailer capacity. So now to increase the trailer to even reach the minimum trailer capacity, I need to allocate more items to the store, so that the trailer can actually physically move to the store. When I want to allocate more than what is required, how do I allocate more? Meaning, for example, if the store is having 1,000 items, okay, and now I have to allocate more than the sum of the demand for 1,000 items, which item should I allocate more? For example, there is paper towel, there is shampoo as a choice. Should I allocate more of shampoo or should I allocate more of paper towel? How do I make the decision? Right? That is called forward looking, which is I am choosing to allocate more than what is required for the very reason that the trailer can actually physically move to the store. So I want to allocate more via which for those items which has higher demand for the store. That's this forward looking. I mean, I'll kind of explain this a bit more. So it's like forward looking inventory allocation system. It leads to better utilization of labor and trailer. And we designed the system as an optimization framework to the length of an optimization framework. And lo and behold, our optimization framework leverages this concept of submodularity and optimal transport theory, which I just described. So the idea is we are able to come up with a better inventory allocation plan by coming up with an objective function, an instance of MILP. That MILP instance has all the properties of submodularity and optimal transport theory, because of which we can come up with a faster solution to that objective function. So here the contribution is twofold. One is to even design an objective function for an inventory allocation engine. This doesn't exist. And we are kind of the first one to propose that one can think of inventory allocation planning through the lens of an optimization framework. And secondly, the optimization framework can be efficiently solved using the concept of submodularity and optimal transport theory, which I described earlier. And thirdly, one other thing what we have shown here is we again have this this linear instance, which we are able to transform to an instance of something called a capacity constrained optimal transport. This is nothing but an instance of optimal transport with one additional constraint. So this transforming an instance of an LP to an instance of a COT itself is new. The advantage is LP, as I said, is cubic complexity. But the COT, which is again is a variation of optimal transport, can still be solved in linear complexity. So the question would be is, what kind of linear programs itself has this notion which can be reformulated as an instance of a COT problem? This is more like this is an open question, and it could be of independent interest to researchers in the field of operations research. So at least for this, we are able to prove that the linear instance does, the linear program, coming out in the inVals framework has certain properties which can be leveraged to transform it to an instance or COT problem and amenable to faster solution approach. This assumes significance given that LP formulations appear in plethora of problems studied in operations research. This is more like an open question, which I don't have a solution. The open question is, what is the structure of linear program which is amenable to such kind of transformation to an instance of a COT problem? Okay, so
that means all LP cannot be transformed to a COT problem, right?
Yes, all LP cannot be transformed. Yes. The question would be, what kind of, what is the structure in LP which can be transformed? So I will kind of skip all this. I don't think so I'll have time to go over, these definitions. I'll just talk about the objective functions first, right? Okay, so all this we have to cover. Okay, so the inventory allocation problem, which is about what portion of inventory has to be allocated to what store. So that some aspect of labor capacity at the store, the trailer capacity, which is both the minimum and the maximum, the demand at the store, the business constraints are all met. So we designed this objective function, which I written here, to kind of solve. So this objective function also has this dual type variable. Here, that's a simple pollution here.
Loud.
So this x is an integer variable kind of feedback. I'm getting a feedback. I think probably one of the things is not muted.
Oh yeah. Some disturbance. So you can continue.
Okay, so this is an objective function which we designed for solving the inventory allocation. This objective function has a similar structure to MILP, which I spoke earlier, where so we are solving for two kind of decision variables. One is this D. The D dictate what portion of demand. D is what quantity of item is allocated between for the store I and the item J. Dij is what portion of demand is allocated. The T is a time period, which is when I'm going to allocate a certain portion of demand for tomorrow, certain portion of demand for day after, certain portion of demand for 2 days later. Right? I'm going to look into the future. The very reason why I have to look into the future is because sometimes I might have to allocate more than what is needed immediately, so that the minimum capacity of the trailer is met. So I'm going to allocate items for a store. I is the store, J is the item for different time periods in the future. Okay. When I'm going to allocate items in the future, I want to allocate those items which are going to be sold faster at the store. For example, if a store is not even selling paper towel, okay, if you allocate more of paper towel to the store so that I can at least hit the trailer minimum capacity, which can be done. But the problem is the paper towel is going to be physically be at the store for a longer duration of time. So the physical storing item in the store is expensive. It leaves something called a maintenance cost. So I do not want to store items at the store which are going to be sold much over a longer period of time, which is called something called a days of supply, which is for how many days is a particular quantity of item will be used to meet the demand. Items which have longer days of supply basically means that item can be used to, that quantity of item can be used to meet the demand for a longer duration of time, which is bad. So we want to kind of allocate more of those items which are going to be stored in the store for a shorter duration of time, so that the maintenance cost is minimal. Okay, so long story short, this inventory allocation problem again can be solved by solving this optimization framework, and this optimization framework has the same structure of submodularity and optimal transport theory, where this term has it has this integer variable. Here integer variable is x, unfortunately not y, whereas this integer variable is number of trailers I am going to allocate to a store. Okay. For instance, it could be the case that, okay, for store 1, I'm going to allocate 2 trailers. When I allocate 2 trailers, I need to ensure that the trailer 1 is filled to the brim, max capacity, and for trailer 2, I am at least able to hit the minimum capacity in the second trailer. If I'm not able to hit the minimum capacity in second trailer, I would rather allocate only first trailer to the store. Because the second trailer, even though I assign it, if I'm unable to hit the minimum capacity, the second trailer is not even going to physically move to the store. So the question would be then how many trailers I need to allocate to a store. That becomes the integer variable we need to solve. Once we have this, the Dij is the continuous decision variable which we are solving. So this has the similar instance of MILP. Okay. Once I give this set with the number of trailers to assign, this becomes a linear problem. So this linear problem can be reduced to an instance of a capacity constrained optimal transport problem, which is what we have a theorem which says that this linear problem, which is this one, which is this one, can be with addition of multiple pseudo variables, can be represented as a capacity control optimal transport problem, which has this structure, which is again some kind of profit maximization. It has the supply constraint, it has the demand constraint, and it also has constraints for has a point-wise constraint. This point-wise constraint is what we call as capacity constraint. That is, each decision variable has a constraint upper bound for each of them. This is called a COT, capacity constraint optimal transport. Okay, so this was surprising result for us to kind of take the linear program, transform it into a COT. Once again, this COT also has faster approximate solution. So which was I had I had the reference here. I don't know if I couldn't find it. So again, so this leads to coming up with faster solution mechanism. So and then we compared with different ways of allocation, and then to assess the quality of our allocation mechanism with respect to labor usage and transportation usage. So, and then we also use different kinds of solvers, where we use the MILP solver, and we use this linear solver, where this g of x, which is again a linear program, is solved using this LP, and we use the COT solver. So this was a COT instance. Okay, and here also there are different ways in which that can be solved. and the COT problem is available in this reference. So once we design this, we notice that I'm just flashing the results. Unfortunately, I'm unable to go over it in detail. So we basically saw that our inventory allocation engine, which is this D, which is what invals is, has higher Taylor utilization, and it also has much higher labor utilization. So, and then it also lead to much efficient runtime solution. So our algorithm. So once we designed this objective function, we were solving it using multiple solution approach. The DRM is the one where we solve it as a COT problem, instance of a COT solution, and we see that which is the DRM as the least runtime compared to solving it as a linear program. So, the crux is we're able to come up with an objective function for the inventory allocation problem, the solution to which led to much better labor and Taylor utilization, and we are able to come up with the solution approach of using the concept of submodularity and optimal transport theory to solve the objective function, which led to efficient and fast computation. Yeah. So yes, that's the end of my presentation. So, any questions?
Thank you, Dr. Karthik. So it's a good one. I mean, so one thing just I would like to ask, and this, as you said that theorem also you have proved that some kind of the particular kind of LP can transform to cut problem, right? And is there any such things like example or class of example where which LP are not transformed to cut problem?
No. So actually, that is an open problem. What we showed is the LP that occurs in this inventory allocation problem can be transferred into a COT problem.
Okay.
So what is the more general thing is to come up with a theory behind it, like what kind of LP instances is amenable to COT.
But is there any example particular that this problem cannot be done COT problem? No.
That is kind of easy to come up with. Yeah, meaning generally a general instance of LP is not transformable to COT. Meaning because the COT should have this very specific structure. Meaning because see the constraints are very limited. This is an LP, right? But the constraints there are only two kinds of constraints, or even three kinds of constraints. If we have any kind of additional constraints in it, it will not be transformed into a COT problem.
Okay.
So the theory behind the transformation is something it's quite interesting to study. Meaning what the structure is in LP, that because we actually thought this LP could not be transformed, but by adding a lot of pseudo variables, we were able to transform it. So it is not very clear to us what is the structure that makes this transformation even possible.
Okay. So participants may ask some questions. If you have any queries, please kindly interact with the speaker.
Sir, I have a question.
Yes.
So I have a situation actually. So when we have an imaginary situation where a warehouse has a limited inventory of eatable items, like it has some short expiry date, and multiple stores require the same item. So imagine a situation in which one store has high demand but very limited storage space, whereas the second store has low demand but ample storage. Then how does your system prioritize this allocation of the item? Considering we should consider both urgency and also the fulfillment of demand, right? So how do we
that's a very good question. Yes. So if an item has low storage, so even though if we are able to send the item to the store, okay, the store cannot physically hold that item. So what will happen is the store will then discard it.
Okay, sir.
So the physical capacity of the store has to be brought in while deciding how much to be allocated. That more like a hard constraint. And this happens all the time. So even though there is enough demand at the store, but either the store should kind of create more space for it, meaning that becomes a separate optimization problem altogether. Otherwise, even though we have sent a lot of items to the store will not be able to store it. So the capacity becomes more like a hard constraint. And secondly, if the capacity can be arranged between other items, that can be framed as another optimization. In the sense that, okay, I have one capacity of the store where multiple items compete for it. So now I need to then decide, what item to store to what capacity. So that decision can be made by some aspect of profit maximization. For example, if I'm able to hold, let's say, bananas, and bananas are, sold in huge numbers, leading to high profit, compared to holding paper towels. But paper towels and bananas are not competing for space. That has to be framed as another optimization problem for solving for space. So right now, we are not doing that. For us, it is assumed that the space for banana is already given. Now, for bananas, what will happen is the days of how many quantity I can hold bananas has to be very limited for one day. So if I'm going to allocate banana for second day, that will just not cut it because bananas are perishable. So those aspects can also be brought in.
Thank you, sir.
Sure.
Any other participant can ask questions.
Hello, sir. Good evening, Karthik, sir. I had one question with respect to the commercial solver for MILP, right? So I have heard of LP solvers, which which will give optimal solutions because linear programs as such are polynomial time solvable, right? But MILP being an NP-hard problem, what does it mean by commercial solvers? Do they give any optimality guarantee, or are we still looking at the approximate solutions by the commercial solvers? Because we are actually comparing our solution, that whatever solution, the method and solution that you have proposed, you're actually comparing it against a solution given by the commercial solvers, right?
Yes, that's a very good question. So the notion of what is global optimality itself is questionable. So what happens is commercial solvers. So the commercial solvers also come up with a lot of configurable parameters. The configurable parameters will be more like how much is my solution changing with iteration. That's more like a threshold that has to be kept. For example, if I say, okay, the solution does not change by more than 0.01%, that is my solution. So those are configurable parameters. The smaller those numbers are, the longer the solver will run. So what is the global optimal solution is determined by those configurations which we need to set. So what we assume here is, by setting up those configurations, whatever the solution that the commercial solver spits out to us is regarded as the globally optimal solution. So if a configuration is set in such a way that the solver takes only smaller time, that may not be the globally optimal. And certain aspects of global optimality can also be determined by this duality, where if you look at the duality gap, since LP for LP problem, the duality gap is 0. So if we can look at duality gap and see that, okay, the gap is 0, then or the gap is very small, and whatever solution we obtain can be regarded as globally optimal. One way to verify this.
Got it. Yeah, so the one way that we should be looking at the optimal is probably the lower bound, which is by the LP, actually converting the MILP into an LP and then setting the lower bound there, right? Something like that. Is that correct? But we will not be able to achieve it using the commercial solver, I'm assuming.
No, we cannot convert MILP to LP, right? Because the LP will not satisfy, may not give us integer solutions.
No, that is true. But just to set the lower bound is what I was thinking. The lower bound, generally, even for ILP,
Well,
when
that's
we
true,
want to have a
exactly.
lower,
Yeah, the LP will give you the lower bound. Let's say if you're minimizing it, the LP
yeah,
will have lower bound because the integer constraint is not
relax.
there. But the lower bound LP might be way lower, and
Got
MILP might not even be able to hit the lower bound. So, one way to check an optimality with an MILP solver is this notion of duality, which
Okay.
is generally taken care by these solvers, meaning they already take care of all this. So, in most likely, the solution that they spit out will be closer to global optima. Closer.
So, yeah, sorry. Yeah, please go ahead, sir. Sorry.
Yeah. So we just regard whatever solution they give as a global optimal solution, and then we compare our solution to those.
Okay. So the other, I mean, when you are actually calculating using the commercial solver and you're comparing it against it, I'm wondering if, I mean, it may not be possible to really give a theoretical approximation ratio for this, right?
Uh, Theoretical approximate
Approximation
rate.
guarantee. For instance, say the solution that we get is within the given bound of the optimal, right? I mean, that's how we define the approximation ratio. So,
Yeah, for certain things it can be done. For instance, the submodularity aspect it can be done. The submodular functions are those for which theoretical approximate guarantees are available. I think it is 1 minus 1 over E. So there are certain portions of the solution framework where theoretical guarantees are available, and there are certain portions where it is, where still we are yet to develop it. So it's a mix of both.
okay. So I don't have missed something crucial. That I was talking about the facility location problem with respect to this. Now coming to the invals, that is not an NP-hard, or is it? I mean, I don't remember seeing the complexity part of that.
It
Invals is
actually it is because invals also has this
MIL.
the x is integer variable, right? It's again of MIL. When
Oh,
solving this will be NP hard.
okay.
Okay.
Okay. Fine. Yeah, sure. Okay. Thank you very much, sir. Thanks.
In case if any questions from participant, you can please go ahead. So, okay, if you don't have any question or if you have any questions later also, you can please reach to us. And also Dr. Karthik can be reachable. If in case if you are interested, we can share the mail ID. So then once again, we thank to Dr. Karthik for sharing a good, very excellent talk and with all practical relevance. So thank you again.
Thank you everyone for your time. It was a pleasure to give a talk. Yeah. Thanks for your time.
Thank you. So with that, we can close these sessions. And tomorrow we'll have so our 2 sessions will start at 6 p.m. So we'll meet tomorrow then. See you then. Good night.
Good night.
Good night.
Bye.
Bye-bye.
अच्छा अच्छा